All right, so this was a useful slide to stop at earlier because we can also recap roughly what we discussed. So we talked in the first part about the quantum PCP conjecture, which roughly is about encoding quantum computation into low energy states of a local Hamiltonian such that you can read the answer at least, maybe more. And then Friedman and Hastings, they, observing how difficult this question was to answer, they distilled a very nice question, the NLTS conjecture, which was focusing on one source of complexity, that's circuit depth, and trying to rule out the presence of any Hamiltonians for which you don't have any low energy state with constant circuit depth. As we discussed also in the previous part, these Hamiltonians can't live on a lattice, because on lattice you always can cut the lattice into parts and come up with constant circuit depth. All right? So we discussed that NLTS, which is this conjecture, is a necessary consequence of quantum PCP conjecture, assuming that QMA not equals NP, which makes sense. So the goal for the remaining part of this section is to try to understand why quantum codes are an important source of hardness for NLTS conjecture. One way, of course, if you can prove quantum PCP and you assume QMA not equals NP, then QMA not equals NP provides the source of quantumness, a source of hardness, which would imply NLTS. But given that we don't have this, where do you look for hard Hamiltonians? Where do they exist? That's the thing. So that's what I'll talk about for the remaining part of the section. Before that, any questions about what we discussed so far? Yes. Yes, yeah.
Could you recap this thing you said about like two different sources of hardness and just make that really clear again, please?
Oh, two different sources. Oh, yeah, I was just saying. So QMA not equals NP is basically saying that quantum computation is hard classically. So that's what I'm referring to as source of hardness. Just a term to keep in mind for us. But are you referring to something else?
And you said something like the question of NLTS is a question of whether there's like any other source of hardness.
Right. So you want to construct an NLTS Hamiltonian, and in the process you will prove that all the low energy states have high circuit complexity, high circuit depth. What's the reason for that? It's not QMA equals NP, not equal to NP, because we don't know how to use that. So what else should we use? That's what I'll talk about, basically. Yeah. Thanks for that. All right. So Hastings and Friedman, in the paper where they put this conjecture, they already recognize that maybe quantum codes should play a role in this. And let me spend this slide and the next to kind of get to that a little bit. So what they proved, actually, just as a side remark, is they proved a one-sided NLTS in which the Hamiltonian was in two bases, x and z. In the z basis, it was a very non-local Hamiltonian. But we want totally local Hamiltonian, of course. So this is not an NLTS. But let's try to understand pictorially. This picture will carry over to many slides. So let's spend some time trying to understand this picture. Here's the reason why intuitively quantum codes seem like the right thing to work with. So as a recap, what's a quantum code, specifically quantum CSS code? It's a stabilizer code, and I'm thinking of LDPC, which is low density parity check. All it means that the stabilizers are of constant weight. The stabilizers act on a constant number of qubits. So you have stabilizers that are X stabilizers or X checks, which are, all the poly X matrices of the form X to the A, where A is a n-bit string, which comes from some row of some other classical parity check matrix Px. And Z is similarly defined. So you take two classical codes. From one, you make X checks. From other, you make Z checks. And X and Z have to commute. So these codes have to be mutually orthogonal, things like that. That's fine. But roughly, that's what you do. So once you do that, you get a quantum code space of certain dimension. It encodes 1 or 2 or whatever, that many qubits. Take any quantum state in that quantum code. Look at that quantum state in the X basis and also look at it in the Z basis. So we can do two things. Basically, one way to look in the X basis is to do a measurement of the quantum state in the n qubit, apply a Hadamard and then do a computation basis measurement, something like that. But let's say you look at the quantum state in the x basis. What you'll see is that all the strings, the bit strings that you see in that x basis, will have a very specific property. So here, these squares that you see from here and later, basically are supposed to represent the space of n-bit strings. The space of n-bit strings is a big space. It's called Boolean hypercube. It's very, very large, 2 to the n dimensional. I don't plan to represent that at all. But think of it as, having n-bit strings basically being represented here. So what happens is that in x or z basis, in both bases, what happens is that the quantum code words are always going to be restricted to these circles. And the distance of the code, the x distance, is the distance between these circles, and the z distance is the distance between these circles. So that's what happens in a quantum code. So every code word in the x basis will have its strings clustered in these tiny circles that are far away. Similarly in the z basis. If you have a classical code, then you only have z basis, you don't have any x basis. These circles are points. Classical code is a collection of points which are far away in the space of all n-bit strings. In quantum code, you don't really have that luxury, but what you have is that these are these thicker circles which are far away. And that's all you need for quantum error correction. All right? So we'll just be keeping this view in mind. And you can also think of these as cosets and stuff, if that helps. Each of these circles serves as a coset, roughly. But yeah, the structure is very complicated, but I'm just doing this cartoon drawing just for convenience for us. All right. So a very important step was taken by Elder and Harrow in trying to prove this conjecture in 2016. And what they showed is a very interesting theorem which says that if you have a property called quantum local testability, which I'll define in this slide, if you have the property of quantum local testability with something called as linear distance, then you would have shown NLTS conjecture. Unfortunately, we don't know any way to construct locally testable quantum codes with linear distance still after so many years. So we don't know if this route really proves NLTS or not. But they showed that if this codes existed, then indeed you would have an LTS. So let's see quickly what quantum local testability means. So let's first talk about local testability in the classical world. If you have a classical code which has a parity check matrix P, we say that it's locally testable if every epsilon approximate code word, which I'll define in a moment, is close to a code word. So if the code word is epsilon approximate, then it's close to a code word in Hamming distance order epsilon. Think of epsilon approximate code word is a epsilon energy state of that classical Hamiltonian which comes from the parity check. Roughly, if you have an x, which is a code word, then p times x is always 0. An epsilon code word has p times x at most epsilon n. There are at most epsilon n ones in that. So epsilon approximate code words are the strings that only violate a small fraction of checks in your code. Okay? And local testability classically says that if you have any string that satisfies a small number of constraints, has small energy with respect to your code, then it's also close to a code word in Hamming distance. And what is a locally testable quantum code? For all purpose, it's basically if px and pz are both locally testable as classical codes. If that's the case, then it's a locally testable quantum code. Okay? So what this notion is really capturing is that this notion of low energy that we defined earlier is the same as low error. We discussed that that's not always the case. There are many cases where that's not happens. Low energy is not the same as low error. But local testability is a very strong notion which forces low energy to basically be same as low error. Because, if a string is close to another string in Hamming weight, then to go from the two strings from one to another, you just have to flip a few bits. Flipping bit is an error that you make. And this flip can be achieved with low number of errors. So if you have low energy, then local testability says that you're close to a code word. So to go to that string from a code word, you would have to make few errors only. By the definition of error, if you recall, it was like applying a unitary and stuff. So flipping is allowed. So this was an attempt to prove NLTS without worrying about low energy versus low error. And unfortunately, we don't know how to do it yet, but there are many insightful ideas here, so I'll tell you more about what was shown here. So pictorially, the way the x and z view look like now is that, well, you have as before these these darker red circles, which are the original code words of the X and Z in the X and Z basis, those code words. All the approximate code words kind of cluster around these original code words. They form these nice circles around the original code words. And that's what local testability gives you, basically for free, if you assume that. So all these lighter circles correspond to epsilon or low energy states, low energy strings, and they're all close. All right? So both in the X basis and also in the Z basis. Sorry. So once more, so let's keep that view in mind that if I take a low energy state, look at it in the X basis, what I'm seeing is lots and lots of bit strings which are all clustered around the original code words in the X basis, and similarly for the Z part. That's what's happening. So what happens basically is that if you're given any low energy state of a locally testable quantum code, if you measure in the X basis, you get a probability distribution out, like every quantum state does. And the distribution is dx, and similarly dz is if you measure in the Z basis. So this tells you, local testability tells you that dx is basically a distribution that's supported on these light red circles, and it's close to the original code strings, and dz is also supported on these light red circles and also close to the original code strings in the Z basis. A crucial observation that Elder and Harrow made was the following, that the dx and dz both cannot be supported or within only one circle. So here's a scenario that could happen, which is that dx would be entirely on this circle at the bottom, and dz would be entirely on this circle at the bottom. But that will not happen, and that's precisely what we know as uncertainty principle. If a quantum state is peaked in X basis, it should be pretty distributed in the Z basis. Like, the two bases are mutually, uncertain. So they basically observed that you could measure the logical X and logical Z for these two cosets, and that would be enough to be a witness for uncertainty principle. And using that, you could basically show that it's not possible for this dx to be entirely here and dz to be entirely here. What it means is that dx must be at least one of the two, dx or dz, let's say dx, must be supported on this and another circle. It should be pretty spread on two circles, not just on one single circle. So that property I will call well partitioned. So what well partitioned means is a distribution, it is pretty well supported on two far away things, like the distance between them is distance. So if the distance is linear, then they're still far, and that's what's happening here. Sorry. So now we have now seen the notion of well partition, which Elder Harrow observed that it exists in these distributions if you measure in X or Z basis. That's given to you by local testability. But why is that important? So let's go back to the little quiz that we did earlier for the cat state. And all of you pretty much had the intuition that a cat state, which is all zeros plus all one, should be hard to prepare, and plus state should be easy to prepare. But here's the way to actually quantify it, to actually prove it. The way to do it is that, go ahead and measure cat state in the commutation basis. And similarly, go ahead and measure plus state in the commutation basis. For cat state, if you may do it, all you get is all zeros with half probability and all ones with half probability. But for plus state, you get a uniform distribution in this whole square. So the cat state, the distribution is well partitioned. It's kind of peaked at two far away points. It's partitioned into part of the space. And the claim is that that is the reason why quantum states are hard to prepare by constant depth circuit, cannot be prepared constant depth circuit. So here's a more precise statement. It's slightly technical, but it's basically saying what we just discussed, is that if you have a distribution D and you measure it in some basis, like computational basis or Hadamard basis or whatever, if you can find two sets S1 and S2 that are far apart in Hamming distance, for example, these 2 points, all zeros and all ones, are farthest apart in Hamming distance, they're n distance away. If you can find these things, and the distribution gives a decent probability to the two sets. For example, in this case, the cat state gives half to here and half to here. It's pretty well distributed. Whenever that happens, you can show that the circuit depth needed to prepare psi must be at least log n. That's the statement that you get. And this statement was shown by Elder-Harrow, but we later found also it existed in the work of the authors. Sorry. So what it's saying is that if you can witness a well partition of the distribution, you get a circuit lower bound. So now you can focus on well partition. Where do you get well partition? And if you recall, since either dx or dz should be well partitioned for locally testable codes, you get that NLTS follows from quantum local testability. So to get some intuition about this particular phenomena, it's maybe a little bit like you start with, there's a nice picture of it using moving sands in a desert and stuff. Like it's hard to put sands around to make two peaks instead of just starting from one peak and so on. But I won't get into that. I don't have a good intention with myself.
Can I ask a quick question?
Yes.
Right here.
Oh,
right.
Oh, yeah, there you go. Yes.
So I'm a little confused. So in order for them to be well partitioned, you can't have, for example, like n of these peaks. Like it has to be like constant or yeah.
Oh, n is fine. So take
Okay.
n over 2, n over 2. That's totally fine.
I see.
So if there
Okay.
are n peaks which are all far from each other, just
I see.
choose n over 2 on one side, n over 2 on the other side, and that's totally fine.
But then so when you so this like order of one well partition.
Oh no, S1, S2, or theta. No, the distribution provides a weight of order 1 to both.
I see.
Yeah.
Got it.
So if there are n peaks, divide into n over 2, and this will get half the weight, this will get half the weight, and half is like theta of 1. So
I see.
Yeah.
Okay, thanks.
Yeah. In fact, that's what happens. You get lots and lots of these peaks with tiny weight, but we just collect them together to make sure they're far away from each other. So basically, so the claim here is that quantum local testability with good distance serves as a source of hardness here. Like quantum local testability forces the distribution to be well partitioned, and that gives circuit lower bound. In fact, for a long, basically the main challenge after the work of Elder-Harrow was how do you really get around this local testability, because it's unclear how to go from low energy to low error. Quantum codes are good at dealing with errors, not good at dealing with energies, right? So that's what we know, quantum error correcting codes, not quantum energy correcting codes. We don't call them that. So how do you translate from low error to low energy? And that's really sort of a central bottleneck in this business. So in fact, what Elder-Harrow were able to prove without any assumptions was a no low error trivial states theorem. Since they didn't have any good quantum locally testable code, which we still don't have, they considered what is known as a hypergraph product code. And for that, they could show these similar arguments for low error states, but not low energy, because we don't know whether these are locally testable. Probably not. All right, any questions? Okay, so in fact, so the main point is that really overcoming this issue of going from low error to low energy is what is the main ingredient of the proof of NLTS theorem. All right, so there are a series of results after that, which definitely is important to mention. So in a very nice work, Nirke, Vazirani, and Yuan showed that you can construct no low error trivial states, NLTS Hamiltonians, in one dimension. And you use it by using this idea that has been around in this tutorial for a while, which is that, well, sorry, if you can have, you can use circuit to Hamiltonian mapping to convert, to carry over the quantum computation to ground state of the Hamiltonian. That's what Feynman-Kitaev Hamiltonian does. So, what they did is that they took the circuit that prepares the carrot state itself, and then they used Feynman-Kitaev Hamiltonian to get the desired Hamiltonian in 1D. This can be done, and in fact, it can be made robust to error as well, but not robust to energy. So Feynman-Kitaev Hamiltonian has low energy states which are very, very useless for any computational point of view, but it's probably the case that they showed that low error states are fine, and that's what happened here. And in fact, this 1D structure shows that NLTS is not really the right notion. Because these Hamiltonians can't be NLTS. Okay. So that's really one of the big surprises from this result. And then after that, a work by Bravi, Klesch, Koenig, and Tang showed NLTS theorem from symmetry protection, assuming some X basis symmetry in a classical Hamiltonian. Again, that can't be NLTS because classical Hamiltonians are classical. And let's see. With Chenmanike, we showed a circuit lower bound for 1 over Pauli energy states of various quantum codes, and the new ingredient here was high rate codes needed for entropic arguments. But these are again non-NLTS because these arguments also apply to 2D toric codes, which are not expected to be NLTS. All right. So now I'll talk about the fact that, I'll now get to the giving you an intuition of how does one, how to prove this NLTS theorem. So I'll talk about expansion instead of local testability as the source of hardness. That's the place where hardness actually comes. So for that, in a work with Nicholas Brookman, we showed a weaker version, which is the combinatorial NLTS conjecture. It was in the work of Adler Harrow. And it has some construction that uses EPR pairs with classical Sipsa-Spillman code. And then it uses a tensor network Hamiltonian. So this work is really about classical codes and not about quantum codes. And that seems to be a helpful thing to do. Often, if there's a hard question you want to solve, which is in quantum world, it's good to find a classical analog which also makes sense. It's pretty hard to do that for NLTS because NLTS is a purely quantum question, and classical Hamiltonians always have product states, bit strings. But still, it was possible to come up with a classical question that you could answer and make some progress on this conjecture. So what I'll do is that I'll tell you the key ingredient in this work, which is that this property we're looking for, that a distribution has a well partition, it comes from expansion in the classical codes graph instead of local testability. And then from there, what I'll do is that I will tell you how this carries over to the quantum codes. The quantum version is slightly harder, which is what we proved in the NLTS theorem. It's more difficult to prove because we have to talk about good quantum codes and so on. So instead, I'll focus on this classical code. All right. So let me explain how do you get expansion as a source of hardness instead of local testability. So here's the Sipsa-Spillman code in the simplest form I could draw, and it looks as follows. You imagine a graph on n vertices, and in this graph, you put bits on the edges of the graph. So each edge stores a bit, and each vertex, it looks around a collection of edges. So this vertex looks around this collection of edges. What you want around each vertex is a good code. So each vertex is looking for a nice classical code around itself. And these all vertices are looking for a nice classical code around. So, sorry. So of course, in classical coding, all 0 is always a code word. So you can just set all these edges to all zeros. So if you put 0, 0, 0, 0 everywhere, every vertex will see 0, 0, 0, 0 around itself. So every vertex will see a valid code word, so they're all happy. Every vertex is happy. But now let's go ahead and try to create a non-zero classical code word, a non-zero string. So I go ahead and let's say flip a 0 to a 1 somewhere. So of course, 1 is not enough, so I'll maybe flip a couple more bits to satisfy a certain vertex. So I do that. But then it turns out that there are other vertices which now see a 1, which were connected to that original vertex. So you have to start flipping more bits to make that vertex happy and so on. Yes? Code words, yeah. Oh, no, code words, yeah. I'm talking about code words, yeah. Yeah, sorry. So what I mean is I'm trying to construct a code word of non-zero Hamming weight. Yeah. So what happens is that if you ever put a single 1 in this graph on any edge, that 1 has to propagate throughout the graph in an extensive manner to satisfy all the vertices, so that all the vertices see a nice code word around it. And what happens is that causes basically this well-connectedness of the graph is what causes a high Hamming weight. So what happens is that if you look at this code and look at the code words, the 0 code word is here and all the other code words are far away from 0 and far away from each other. You need to flip a lot of bits to go from one code word to another code word. So given a code word, you need to start flipping a lot of bits to find another code word. And that's the intuition for why these codes are have good distance. Yes?
I have a quick question. How do you decide in which order which way do you order the bits on the edges to actually construct a code word?
That's a good question. So you don't really do it that way. I mean, that's sort of intuition. You can do it in any order. What you use is a notion of a small set expansion. And that tells you that just any set that holds non-zero bits must be a pretty large set. if it was a small set, then it would not satisfy at least one vertex.
Thanks.
All right, but the intuition is basically that a single one propagates throughout the graph. Yeah, and that's because the graph is very well connected with everything. All right. So now what I'll do is that let's start thinking about approximate code words. That is the strings which satisfy all but an epsilon fraction of checks in this code. So the main claim that we showed is that the approximate code words have this property that they're all either very close or epsilon n close or constant apart. So if you draw them in the Hamming cube, they will form these groups. The code words which are close to each other, put them in one group, and you'll form these groups. And what's crucial is that there will be some groups which don't have any original code word inside. So local testability, which these codes don't satisfy, would basically say that these empty light circles don't exist. But despite that, expansion tells you that whatever the case, you will have these faraway circles, which are, some will include the code words, some will not include the code words. So that's how, despite the fact that we are thinking of energy, not error, we still have distance between these circles. And the reason why this happens is very simple, that, well, let's say you have an energy budget of epsilon. You can only evaluate epsilon fraction of checks. So sure, you start with all zeros, let's say, and you start evaluating checks. You can do that for a while, maybe for epsilon n locations. But once you cross that energy budget, you can no longer evaluate any more checks. So the propagation that I talked about earlier would again happen again. So you would just you'd start from some code word here, be around it for a while, then you'd quickly jump to a different cluster which doesn't have any code word inside and so on. So well partition will happen without local testability. So that's the main thing. And that comes from, basically all this come from well connectedness of the graph or the expansion, more precisely the spectral expansion of the graph. Okay, all right, any questions about this? Yes. That direction.
So I'm sorry, I got a little bit confused, but you have this graph, and it's related to the interactions of qubits in your local Hamiltonian?
Oh, so this graph is a classical Hamiltonian.
Or it's okay. So you're using that graph, which is related to some Hamiltonian, to construct a code.
So in this particular context, this graph defines a classical code.
Okay.
And then in this work, we use this graph along with some tensor network-based construction to construct a quantum Hamiltonian. It's not a code.
Okay. So where is, when you talk about flipping bits and you want to get a code word, where's the parity check matrix that you use to determine whether these things are code words?
Right. So each parity check matrix, so the parity check matrix consists of many parts. Each sits on a vertex. And basically, you're looking for, so there is a parity check matrix defined for each vertex.
Okay.
And the vertex will basically compute the parity of the strings that it sees around in some order, some fixed order, and it expects to see a code word.
Good.
A local code word around.
Thank you.
Yeah. Thanks for the question. Okay. So
can I maybe ask?
Yes.
Can you show the last paragraph?
Yes.
So epsilon approximate code words. So I take a code word and I change epsilon n of the edges. Is epsilon n far or theta n closer, far from what?
Okay, so no, so don't do that. Don't take a code word and change the epsilon n fraction of locations. That's error. Think of any string which satisfies epsilon n fraction of checks. The claim is that those strings are either close or far from each other.
Okay, great, thanks.
They may not be close to any code word at all. In fact, this one over here is far from and this one is very far from all the code words. The code words are all in the dark circle, and these are in the light circle, approximate code words. And they can be far. You cannot obtain them from an error at all.
Great, thanks.
Yeah. And in fact, CIPS experiment codes are known to be not locally testable, so you expect this to happen. All right. So So now we have all the tools to kind of see NLTS proof and understand the source of hardness there. So what we use is the good quantum codes. Again, I don't have time to go into that. It's slightly complicated definition. And these codes have linear rate, linear distance, and this linear distance comes from a very strong form of expansion in the underlying interaction graph. So expansion in the interaction graph gives for the well partition for the similar reasons as we saw earlier. But again, one has to worry about the x and z basis quite a bit. So still a non-trivial argument to make here. So what happens is that basically the x view and z view look like this. The x view, basically there are some approximate code words which are close to the original code words, but some are far, and z as well, some are far. And this feature happens without any local testability. And where do you need high rate? You need high rate for uncertainty principle. It turns out that this structure was too complicated for us to use the Heisenberg uncertainty. So we used the entropic uncertainty principle inspired by a prior work that I mentioned. And that entropic uncertainty principle needed enough entropy in the system. That's uncertainty. That's Heisenberg. That's entropic, not Heisenberg uncertainty. But remarkably, in this QIP, you'll see a talk by maybe Louis Golovich and work by Golovich and Tali Kaufman, which in fact figures out a way to use Heisenberg uncertainty principle in this context and give you say that good low rate codes are also enough. So high rate is not needed to prove an NLTS property, which is pretty cool. So you'll see that in this QIP at some point. All right. Sorry. Some open directions. Let me open this cap first. All right. So one very interesting question is, can we go beyond circuit lower bounds? It turns out that quantum codes, any good quantum code, in fact, contains stabilizer states. And stabilizer states are simple from other point of view, right? You can do computation efficiently on stabilizer states. So these code Hamiltonians are good for NLTS, but they're not really hard in all sense. They're easy in the sense of stabilizers. So can we construct local Hamiltonians in which all low energy states are not only high depth circuits, but also they are far from any stabilizer state, far in a reasonable sense. And there's some progress on this in the work by Koble et al. Last year. And there's also a very interesting no energy sampleable state conjecture of Gerbian and Legal, which considers another class of states which allow efficient computation of local expectations. So these conjectures are basically trying to push to a larger class of ansatz, which are easy to describe and also easy to compute expectation value with. And these conjectures are all in that direction. And in the classical literature, I'll tell you in the next section that PCP theorem was proved many, many years ago. In fact, too early, I suspect. And when that happened, despite that, there were lots and lots of work on studying specific algorithms and proving hardness on specific algorithms without assuming P not equal to NP. And these are all of same spirit. So this could be pursued independent of the quantum PCP conjecture question. One very interesting question is, do we expect NLTS property in physical Hamiltonians? Something which is not like a quantum code, but like a Heisenberg model or something like that. And that's very, very unclear because we need to think about non-commuting Hamiltonians, which is hard to work with. And I guess really the main question is, to move from NLTS to quantum PCP, is there really a bridge, or is there a huge chasm between the two still? So we discussed how quantum codes played a crucial role in this proof. So does it suggest that a quantum fault tolerance will also play a crucial role in quantum PCP? And a talk by Quinn Nguyen, this QIP will tell you more about that. But in the next section, which this doesn't want to move. Oh yeah, there we go. Yeah. So now summary of what we saw so far was basically NLTS Hamiltonians, they have super constant circuit complexity below a certain fixed energy. And their existence is postulated by quantum PCP. Hence, proving them means that there's evidence in the favor of the conjecture. Of course, if you could disprove NLTS, that's probably not possible, but that would have also disproved quantum PCP conjecture as far as we care. But that's not the case, so it's a good thing. The Hamiltonians are constructed from good quantum codes, and expansion, distance, and rate feature in the circuit lower bound. Quantum local testability is not needed, and the hardness comes from expansion of the graph. All right, so now we are moving to the third section, where I will talk about the quantum PCP conjecture itself, and I'll talk about what are the missing links in trying to prove this conjecture, and you will mostly see me very, very confused, like anyone else working in this area. So, I'll try to convey that confusion to all of you with pleasure, and that's how we proceed. All right. So, the classical PCP theorem. Here's a statement. You can read it while I drink water. So this theorem proved by Arora et al. Sometime in 1992, I guess, and published later in 1998. It basically says the classical version of what we have been asking so far for the quantum case, that deciding if the ground energy of a classical local Hamiltonian is 0 or large, the constant is NP complete. We know that whether it is 0 or non-zero is NP complete. That has been shown by Cook-Levin long back. But this is a much stronger statement. Sorry. So the way this theorem works is it follows by a robust encoding of classical computation into classical Hamiltonians, and it really strongly relies on error-correcting codes. And PCP stands for probabilistically checkable proofs. And what this means roughly is that, well, if you're given a string or a quantum state, and if your goal is to measure the energy up to some constant precision, you just have to randomly pick up a small number of terms and do that. You don't have to do too much global check. So you can just do a local check and get the answer out. And that's where what this means, that with using randomness, using probability, you check proofs at constant number of places. And it's a strong extension of the Cook-Levin theorem, which is the basis of NP completeness. And in a similar spirit, it's the basis of the theory of hardness of approximation in the classical world, where really optimal answers are known or believed to be true, assuming some conjectures, building on this result. All right. So let me recap again the quantum Cook-Levin theorem, which is the starting point to talk about quantum PCP. So quantum Cook-Levin theorem by Feynman and Kitaev, as I mentioned earlier, it says that basically the answer to quantum computation can be encoded in a local Hamiltonian, or in other words, deciding if the ground energy of a n-qubit Hamiltonian is 0, close to 0, or 1 over n cubed is as hard as doing quantum computation, and it's QMA complete. In fact, this 1 over n cubed is not so important at all. It turns out that a very nice observation by Li Ji Chen, it shows that you can improve 1 over n cubed to any 1 over n to the c for any small c, like 0.00001, as small as you like, just by taking many copies of the Feynman-Kitaev Hamiltonian. All right. So I guess the main discussion point here is that, well, do the ideas from classical PCP theorem really actually suffice to prove quantum PCP, go from Cook-Levin to quantum PCP? And this has been a subject of much debate, and it's like it goes in both directions. In fact, the debate is really interesting, and it has been well summarized in this survey of Aharonov, Arad, and Riddick. I highly recommend reading this, but I'll tell you some of these limitations in lifting a classical proof to the quantum case. So first limitation builds upon what we discussed in the last section, the importance of quantum codes. So let's see why classical PCP theorem really needs classical codes. And the reason is, well, simply because you're looking for a robust encoding. So here's how it works. In the classical PCP theorem, you start with some like a 3-sat instance or something like that. And 3-sat instance on itself is not very robust, because if you flip a bit, you violate a constraint, and then you can't really see much anymore. So what one does is that one thinks of encoding the solutions, potential solutions, into a larger code word, so that the potential solutions, they kind of are far from each other. And in fact, this is precisely what error-correcting code means. And in fact, you need local testability there, again, to not worry about energy versus error issue. So you need local testability as well, almost always, in this proof. So it turns out that there are a lot of constraints in the original 3-sat. They also need to be encoded in this classical code in some way, and they should be able to distinguish between code words. So they sort of serve as sort of logical operators. What's remarkable is that this thing can be done locally. And this, in fact, can't be done in the quantum case, because in quantum case, any two quantum code words look the same locally. They cannot be distinguished in any local manner. So that already is the first bottleneck in trying to go from just trying to use in a brute force manner a quantum code in a manner that classical code was used in PCP, classical PCP. It's just that you can go ahead and encode the ground space of a local Hamiltonian onto some other code, quantum code, but then you can no longer distinguish between the two by any local means. And in fact, looking locally the same is a necessary consequence of no cloning theorem. Necessary for no cloning theorem, sorry, known as avoiding no cloning theorem. Yeah, it's necessary for quantum no cloning theorem. Yeah, sorry for this. So that's already a limitation that shows up in a very fundamental manner. There's another limitation, and that comes from, yeah, sorry. Yeah.
On the previous slide, could you explain the second point a little more? What do you mean by constraints will be encoded as approximate logical operators? Oh.
So you first encode the witnesses. You encode them into some nice local digital code, and then you want to select some of those code words among them to reflect an original constraint in the original system. And you don't really have to. I mean, maybe I was being a bit too general here. You don't have to have them as exact logical operators. Like even if it's approximately satisfied, then it's fine, because then you'll be close to a code word or something like that.
Okay, thank you.
Yeah. All right. So there is a way to prove PCP theorem which was done by Dinur in 2005, and it was believed to be. I mean, people often think of it as a simpler proof compared to the original proof of PCP theorem, and this proof seems, on the outset, very amenable to quantum Hamiltonian tools, but you see soon that it's hard to quantize, and in fact, it's not so clear why. And this really is one of the aspects which seem very confusing about quantum PCP, is that like, why this proof is not so clear. So I'll spend some time on this slide trying to get an idea, but you'll see that I'm also pretty confused about this, more or less. So one of the steps in this proof is that you start with a two local Hamiltonian C that acts on some bits, and go to two local Hamiltonian, classical Hamiltonian, C prime on some similar number of bits, like n prime order n bits. Oh, sorry, but these are not bits, these are dits, some classical things of larger alphabet, like let's call it dits. With D is pretty large but constant. So this transformation has the property that if original C was satisfiable, then C prime is satisfiable as well. And if C is unsatisfiable, it's a typo, then C prime is significantly more unsatisfiable. And it turns out that there is no quantum analog of this statement itself, which is one of the basic steps, or in fact, one of the important steps of Dinur's proof. Many years ago, Aharonov et al., they showed a variant. They showed that given a two local Hamiltonian on n qubits, you can construct a k local Hamiltonian on n qubits such that the satisfiability behaves in the same way. But this is not quite the same as doing this, and it's unclear whether you can do this kind of argument, which is kind of a crucial step in the proof. And in fact, there's a very important work of Brandao and Harrow from many years ago, which kind of explains why quantizing this step of Dinur's proof would be hard. And it turns out that in this transformation that Dinur gives from C to C prime, the degree of the graph increases a lot suddenly. There are lots and lots of connections that you make in the process. But what Brandao and Harrow show is that in the quantum world, high degree actually corresponds to less hardness. Having high degree, it turns out what they show is that for any two local Hamiltonian on qubits, there is a product state which is very close to the ground state with this factor, if degree is significantly larger than the qubit dimension. So high degree is actually a bad thing for the quantum proof, and that already seems very confusing. That, well, in Dinur's proof it works very well, but it seems that if the same thing would work in the quantum PCP context, then one would have, QMA equals NP or something like that, which we don't expect to be the case. So high degree interaction graphs lead to a low energy witness, NP witness. And in fact, this proof is, this proof is really interesting because it captures the it's based on this information theoretic notion of monogamy of entanglement. High degree means that one qubit cannot really interact too much with too many qubits, and things soon start looking classical. And that's what this statement captures. And this has been a pretty big bottleneck for quantizing de Noël's proof. So despite the limitations, there's another thread of ideas in the community of trying to prove this quantum PCP-like statement for subclasses of Hamiltonians, not just any general local Hamiltonian, but something which is more specific. So for example, think of commuting local Hamiltonians, like the toric code or any quantum code is a commuting Hamiltonian. Well, the question of what's the complexity of estimating the ground energy of a commuting Hamiltonian is a big open question in quantum complexity theory. Despite this, one can ask if one can always transform one commuting Hamiltonian into another commuting Hamiltonian such that non-zero ground energy can be increased. The energy gap can be, the promise gap can be increased. And this also seems to be difficult because we don't know any way to do it apart from kind of following the ideas in de Noël's proof. But there, Eldar and Harrow showed that if the graph has too much connectivity, which happens in de Noël's proof, you would in fact start losing quantumness. You would have product states. There's another very nice direction of thinking about stochastic local Hamiltonians, which are complete for the class MA. And for these cases, a very interesting result was shown by Aronovic-Grillo that if you have a low degree Hamiltonian, a stochastic Hamiltonian, then estimating its ground energy up to constant precision is actually in NP, not in MA. And MA is not, I don't know if MA is believed to be equal to NP or not, but this says that a sort of quantum PCP-like thing for stochastic MA, if it maintains low degree, would actually show that MA equals NP, and that's very surprising. All right. Next thread, which is also an independent thread so far, but also a very powerful set of ideas, which is the question of games quantum PCP. And so in the classical world, I'm almost at the end of the slides. In the classical world, the problem of estimating the ground energy of a n-bit classical Hamiltonian is equivalent to the problem of estimating the value of a two-player game, in which involves one verifier and two provers, or two players, in which the question size to the provers is log n bits and the answer size is constant number of bits. And estimating the energy up to some precision is pretty much carries over. And the quantum version of this equivalence is really unknown, and it's not clear whether it's true or not. Of course, this class in the quantum world captures something as large as RE. That's the result of M historical RE. But here we're asking if the provers are appropriately restricted to be not so powerful. Then we don't know if this is equivalent or not. So games quantum PCP conjecture is an independent question in which you ask the complexity of determining quantum value of a non-local game with restricted provers. And as far as I know, Natarajan and Vidic resolve this question up to some polylog loss, but someone in the audience can correct me. I don't know much about this area, but this seems to be a very interesting thread as well. All right, so with that, let me summarize this section. So we talked about approaches to quantum PCP from classical insights, and we see that these approaches face very fundamental limitations, like the monogamy of entanglement or limitations of no cloning, quantum code properties. And that seems, that just makes this question more interesting because it's not clear what you really need in order to prove a quantum version of the quantum PCP conjecture. Especially the classical insights don't seem very helpful. And it's conceivable that these limitations can be overcome by some small tweaks, maybe by considering 4 local Hamiltonians where Baranda-Harrow limitation doesn't apply, or maybe subspaces that are not fully locally indistinguishable but partially locally indistinguishable. But despite these possibilities, it has been difficult to carry forward any useful proof attempt. And also, as I mentioned, the proving quantum PCP-like statement for restricted Hamiltonians like commuting and stochastic Hamiltonians is also a very interesting open question. And it's unclear if those are simpler because you have to maintain that class as you increase the gap. So with that, thanks for listening. And yeah, let me know if you have questions about this. Yeah.
Thank you. I have a question about the sort of NLTS intuitions, or what the consequences are of this NLTS theorem in terms of thinking about the complexity of performing certain kinds of computations. I'm just wondering, we also have at our disposal the ability to perform, say, measurements and then post-measurement operations, and that sort of just changes the rules of the game.
Right.
And in that sense, how much can we really infer about what's hard to do and what's easy to do based on this?
Right. So if you allow measurements and you allow free classical computation,
Yes.
then pretty much the theory of topological order is out of the window, because you can prepare Tory code ground states quickly, and then so same thing applies here as well.
Okay.
Pretty much. So it's not clear why allowing classical computation to be free gives you a class of states that are, efficiently verifiable, because the light cone would still have to be followed. So it's more about thinking about, circuit classes, which are ansatz which are efficiently describable. That's fine, but also efficiently verifiable. And I don't see that if you have a circuit in which you do measurement, get an outcome, and do a classical computation, why is that a notion which would prove QMA equals NP?
Right, I see.
And that's not clear at all.
Yeah, indeed.
Yeah. So that's sort of the thing to worry about. Yeah.
Okay. Thank you.
Yeah. There's a question in the back.
Thanks. You mentioned one result that you can get the promise gap in the local Hamiltonian problem to 1 over n to the c for any c. Could you give some detail how that worked? I couldn't find that reference.
Oh yeah, so it's it's a unpublished work. Yeah, sure. Yes. This one second. It's basically about changing n to something larger. That's all. So, yeah, it's a pretty simple and nice observation that if you take a Feynman graph Hamiltonian and take like n to the billion copies of that, then you're thinking about m equals n to the billion 1, right? So your promise gap is 1 over n cubed, which is 1 over m to the 3 over 1 billion 1, and that's a small constant. So as a function of m, you have reduced the promise gap, but of course, it's still the same thing. It's 1 over n cubed. That number hasn't changed, but n has now blown up to become a much larger number, m.
Or is this like this idling trick where you like...
It's a padding kind of thing, yeah.
Oh yeah, so you repeat like an identity gate a lot of times in the beginning, then a lot of times at the end?
No, it's not. It's just take
that?
any Hamiltonian and make many copies of the Hamiltonian. It's that kind of argument. And just the promise gap doesn't change because it's a relative promise gap, number of terms. The ratio is same. So yeah, promise gap stays 1 over n cubed, but then it becomes very small as a function of number of qubits. So as long as polynomial transformation is allowed, you can take polynomially many copies of the Hamiltonian, so you stay.
Okay, thanks.
Yeah.
I just have a follow-up to the previous question. How do you take many copies of the Hamiltonian without increasing the number of terms?
Yeah, so number of terms increases.
Okay.
So n gets replaced by something larger.
Okay.
But the promise gap is still 1 over n cubed.
Oh, okay.
But n is like m to the 1 over trillion.
Okay,
so just put n there. So it's a simple padding argument. It just says that really what matters is 1 over that sort of is the reason why computer scientists define everything as poly n and don't care about it's n cube or n square, because simple padding arguments can change the exponent. That's all.
Thanks.
So yeah.
Hi, I'm really not so familiar with this area, so thanks for the talk, giving a very good overview. I am familiar with the Cook-Levin theorem and how it's used, as a target for reductions. So you want to prove a problem in NP, you reduce it to satisfiability.
Mhm.
Could you just explain how the PCP theorem, the classical one, is used? You mentioned it's used in approximability results.
Yeah.
And if we had a quantum PCP result, like what might we also be able to use that?
All right. So one would definitely be able to use quantum PCP as classical PCP for hardness of approximation. And the main question is whether that would still lead to the kind of amazing theory classically. So classically, the PCP theorem has been kind of pushed to the limit where people know optimal hardness of approximation for all constant satisfaction problems under some assumption called unique games conjecture, things like that. So that optimality is, I mean, far, far away for us, and it's unclear if we would get somewhere there. I mean, we don't even have a proof of quantum PCP conjecture yet, so we don't know. But yeah, but one would definitely expect a similar kind of activity if one were able to prove this. Yeah. Yeah.
Could you tell us more about the monogamy of entanglement barrier?
Right. So let's see. Get there. So the main thing to focus on is the statement of Brandauer, which says that if you have any graph, a two local Hamiltonian in which each qubit interacts with many terms, then there is a product state which is sort of low energy, and the way you obtain that is sort of trying to prove monogamy of trying to prove some kind of monogamy statement. So you take the ground state, you measure it in some basis, and you get a family of product states. And it turns out that any qubit cannot be highly correlated with too many qubits in that state. And yeah, but I don't know if I'm answering the question. I'm just stating facts. It's basically the intuition that you can't expect a quantum state to be entangled across many places, so it has to be separable across most of the edges. The hard part is how to come up with a single consistent separable state for all the edges, and that's really the clever trick. But on the face of it, one qubit is looking at many qubits. It would stay highly kind of separable at most for the most pair of qubits. Yeah.
Thanks for nice talk. In the classical case, classical PCP and locality testability, this is highly connected. But in the end, it turned out that NLTS can be shown without quantum local testability in the end.
Right.
And then now suppose we in the end have quantum local testable code. What could we expect toward quantum PCP? Yeah, what's the opinion about that?
I see, right. So do you expect that quantum local testable codes would help in quantum PCP? And I expect that to be the case, because if you have a quantum local testable code, then you have this very nice notion that error and energy are the same thing, pretty much. And that's just a very convenient place to start. So you might be able to just start thinking about only in terms of errors, and then a lot of things can happen after that. Yeah, but I don't know what exactly, but I expect this to be useful.
Okay.
Yeah.
Thank
you. Yeah. Go ahead.
Thank you. So the classical PCP has close connection with interactive proof systems. So I was wondering whether the NLTS theorem has any connections with quantum interactive proof systems.
Oh, it doesn't. It doesn't have any connections with that, except the fact that codes are probably. But in the quantum interactive proof, I don't know if there are codes or not. I mean, I don't know much about that area, unfortunately. Sorry.
Okay, thank you.
Do we have any last questions from the audience? All right, if not, let's thank Anurag again for the great tutorial.
Thank you.